Salutations, fellow chemists. Welcome. Today we're going to be looking at a classic exam question, which is stating the difference and similarities between the plum pudding model and the nuclear model. Before we get started, let's have a look. The plum pudding model states that we have a ball of positive charge with electrons randomly distributed within that ball of positive charge, and our nuclear model has a nucleus, that's why it's called a nuclear model, and a cloud of electrons around it. So do not get this one confused with the planetary model where the electrons are in shells. For the nuclear model, they are not in shells, they are in a cloud. So let's label these very quickly. Just grabbing a pen. So here we have the plum pudding model. Plum pudding model. And here we have the nuclear model. Okay, you'll be able to tell me that the scientists associated with these here, on this side we have J.J. Thomson, and for the nuclear model we have Ernest Rutherford. So later on in this video, what I will do is show you the experiment that led to the changes from the plum pudding model to people accepting the nuclear model. So let's answer the question now. Okay, so very quickly then what I will do is pop in our similarities, if I can open this pen. There we go. So we have the differences. I'll put differences first. And if you have a look at these two here, you can see there is a nucleus in the nuclear model, whereas the plum pudding model does not have one. So here, there is a positively charged nucleus. Positively charged nucleus at the center in the nuclear model. And because we're comparing, you need to use comparative words, so I'm using the word whereas. There isn't in the plum pudding one. The plum pudding is a ball of positive charge. What else is the difference here? Another massive difference, if you have a look between these two, is the electrons here are in a cloud in the nuclear model, whereas the electrons are randomly scattered in the ball of positive charge in our plum pudding model. So let's write that down as well. Electrons in a cloud for nuclear model, whereas they are randomly distributed in the plum pudding model. Okay, we're running out of space a little bit here, but luckily that is us done for the differences. Let's move on to the similarities. I'm going to grab a green pen for that. And hopefully this is easier to open. Easy. So now we look at similarities, and this is easy to see. You can see here they still have electrons in both of them. Both of them talk about negatively charged electrons. However, the only thing that's different is this does not take into account a nucleus. This does. Okay, so we can still say that there are electrons present in both of them, in both models, the location of which is what changes. The other thing you can see here is we are assuming that the charges will cancel out. So all the positive charge and the negative electrons will cancel each other out. So both models propose a neutral atom with charges cancelling out. And that is it for the question itself. What I am going to do, moving over to this side, what I'm going to do for you very quickly though is explain the experiment that led to these changes and led to our understanding being a lot more developed. So stay tuned, we're moving on to that. And just like magic, we're in the explanation stage here. So what you need to know is we're looking at the reason why we go from the plum pudding model to our nuclear model over here. So this will be the plum pudding model. Let's label that for you. And underneath we have the nuclear model. So the experiment responsible for this is called the gold foil experiment. And what happens is you fire high-speed nucleus of a helium atom, and you're firing that straight at a gold foil. So in this case, because we removed the electrons from the helium particles here, they are now charged and they are ions. So we have 4, 2, helium nucleus, which has a charge without the electrons there. So I'm going to represent these as tiny positive particles firing at our model here. So let's start with the first one. And these are our alpha particles. So alpha particle represents our high-speed helium nucleus here we spoke about before. And if you were looking at the plum pudding model, what you would be expecting, because we have a diffuse section of positive charge with random electrons scattered within there randomly, this should go straight through. Because the positive charge is not that strong, we will not be getting, let's draw that a bit clearer for you, we will not be getting much deflection. So some will deflect a little bit, but most of them should go all the way through. However, if we do this for the nuclear model over here, so focusing on the nuclear model, we'll get some deflection over here, a lot more than we see for the plum pudding model. So I'll do that again, showing you even more deflection. We will get some of them going to the nucleus and turning all the way back. And most of them, just like we saw in the previous one, should be going straight through as well. So what we're going to do is summarize these observations and give you the reasons for them very shortly. Just switching pens. Okay, perfect. So moving on to the observations we see here, the main observation. So I'm going to write that here. So observation number 1, which is the same as what you'd expect for the plum pudding model, is that most particles go through, most alpha particles go through. They go straight through. As we saw for the nuclear model here, what you'll see also is that some are deflected. And the thing that we definitely do not see in the plum pudding model is the last one. A few of them, are reflected. And reflection is different to deflection. And I'll tell you that very quickly. Reflection is going to the nucleus and coming all the way back. And deflection is just having the path change very slightly. So what do these mean? Let's explain this on the side here. So explanation. First one, the fact that most of our particles are going straight through tells us that we have mostly empty space here. The atom is mostly empty space in the atom. And the second thing here, the fact that some of them are deflected, and you can see slight deflections here, is because we have a positive charge on our alpha particle and a positive nucleus. So we're expecting them to repel each other, and therefore we must have a positive nucleus here. So the nucleus is positive. And the very last one here is how a few of them are reflected, which definitely does not happen in the plum pudding model. And that's why we had to change the model to the nuclear model. And that's because there is a concentration of mass in the middle, so that nucleus is very dense. So let's write that down. The nucleus is very dense. And what I mean by dense is that there is a concentration of matter in the middle of our atom here. So hopefully that's clear to show you why we had to move from the plum pudding model to the nuclear model. And that's all because of the gold foil experiment. So make sure you like, make sure you follow and subscribe to the YouTube, and I will see you in the next video.